getting our webinar software running, making sure we're squared away. So I think a couple people seem to be trickling in still, but we're going to get underway. So a little bit, just a quick agenda about what we're going to talk about today. We want to talk, quickly get through an introduction to data science for anybody who is just getting exposed to a lot of the concepts we're talking about. And then we're going to talk about the mechanics of how value gets created and how organizations extract value from data using data science methods. And then we're going to be talking about designing a data science process that is optimized for successful outcomes. So by way of background, my name is Austin Ogilvie. I'm the founder of a company called Yhat. We help data scientists build and deploy predictive apps. And we were founded in 2013, so we're a startup, and we're based in New York. And some of you may know us from the community. We have hopefully pretty solid social media presence and community presence, try to be contributors to a lot of open source projects. And we have a blog. Maybe a lot of you have seen it before. So quickly, the crash course in data science. When we're talking about data science today, the definition that we're going to be working with is sort of broad. Anybody using statistical programming techniques and a combination of machine learning, research skills, and programming to solve business problems. And we're going to be focusing on what distinguishes data science from just the component pieces and the tools that are in use, being the applied nature of the field as a whole. So data science is more than simply interesting research. There is always an end user in mind, and a lot of the time, the primary focus of data scientists is optimizing decision making in a more tactical sense than, say, business intelligence would be. So, as an example, if we're talking about optimizing a user experience for somebody on the Netflix web app, the end deliverable is a stickier user experience. Carl wants to watch a movie. Here are some movies, Carl. Data science is less about explanation a lot of the time. So sometimes explanation is not even a fundamental requirement of a data science project. The motivation, again, is not that we want to tell Carl or anybody that two users have similar movie preferences, but instead to make recommendations for a particular user. So what are some of the principal challenges that data science teams encounter? Well, for starters, there's been a pretty fierce investment in data science and data infrastructure and big data tools over the past 10 years, certainly over the past 5, and growing rapidly. But unfortunately, the success rates that companies are reporting is pretty much unanimously less desirable than we would have hoped. So 30% of companies, according to one, I think it was a PwC report, said that they have seen success through their data science investments. There are others that are out there that sort of match that same sentiment. So what's going on here with all of the hype and interest in extracting new business opportunities and capitalizing on locked up value that's in data? Why are companies having a hard time actually realizing it? We think that it basically boils down to two fundamental obstacles. The first of which is a lack of understanding. So data science is an esoteric space that a lot of people have a very, very challenging time understanding. So that could be business-oriented people or less technical people not understanding some of the core concepts. It could be misunderstanding the way to represent a problem, or misunderstanding the context in which a solution needs to operate to be practical or to be viable. But generally speaking, there's a lot of moving parts, and there's a lot of people that need to be included in whatever a data-driven solution or a data-driven product is. And there's therefore a lot of opportunity for people to get their wires crossed and to not understand one another. And the other is difficulty in experimentation. So the costs, it seems, for most companies right now of running an experiment are actually quite high. And what that basically means is that if you're exhausting a lot of resources to run an experiment, and experiments don't tend to be super successful right out of the gate, appetite for and commitment to data science really sort of falters, and people sort of have a hard time doubling down on certain things or investing further. So to give you a more sort of contextual example, this is a pretty standard operating paradigm that we see across the board at companies that we're talking to. Sort of the business owner, stakeholder goes to the data scientist and says, we've got a problem associated with X, Y, or Z, and the data scientist is sort of given this somewhat nebulous, or at the very best, crudely shaped representation of a business problem, and sort of the business trusts that that individual is going to be able to perform some sort of magic and come up with a solution to whatever it is. And a lot of the times when insights are discovered or unpacked by a data science organization, the byproducts are super difficult to articulate back to the initial stakeholder that first requested or expressed a need or a problem in the first place. And so it's unclear to the person who has the problem exactly why a solution may be a good solution or a bad solution, and they can't constructively provide a lot of great feedback on the work that's been done. At the same time, there's a disconnect that lives between the data science world and the software engineering world. And when companies don't blend the roles between these organizations, a lot of bad things tend to happen. And there's sort of a language disconnect and a tools disconnect, and articulating where certain data science code, R, Python, SAS, MATLAB, et cetera, need to be integrated, and how a lot of the mechanics of how models work under the hood is not expertise that you typically find on a web or a mobile or CRM development team, and so on and so forth. And so this throw it over the wall approach, where execs expect magic out of data science, and data scientists have mixed degrees of support from application developers, and application developers are unclear about what the requirements are, and so on. There's sort of a lot of different objections that you can see that cause a data science project to stall at any point throughout that entire narrative. And some of them that perhaps many of you are familiar with are, we shouldn't do the data science project because the benefits are not there, or we're skeptical that it's going to work, we don't trust that this is an accurate forecast, we think it's too complicated or expensive to do it, we just don't see the ROI potential of the project. These are sort of the features of a stalled project, and why various stakeholders may, reasons they may give you to stall a project. So what is fundamentally going on here? And I think a good place to start any sort of dissection about what causes this type of throw it over the wall approach is that there's so many different things that need to happen from the point that data is collected till the point that you've delivered an operational production solution in the form of something that is useful to an internal employee, or useful directly to a customer within customer-facing app. And like any raw material, as you do work on it, the data becomes more and more valuable. But as you are achieving this valuable, as you accrue value over time, the amount of work that goes into each of the fundamental steps is not necessarily mapped directly one-to-one with the value that's created as you go. So if data starts out as an unrefined raw material, and at the end of the day it needs to become something flashy that creates ultimate value for a customer, you may do an inordinate amount of work to get the data into a clean format, but the value or cause value to appreciate nearly as much as you would like it to, given the amount of resources it takes to perform the activity in the first place. And so I think this is sort of the fundamental mismatch in expectations across the board. So different teams are thinking about different pieces of this puzzle and care about different things on different timelines, and getting this world is very, very tricky. And that's by and large why data science is such why being a social organization is so fundamentally important for any data science organization's success. So to the extent that you can get a team aligned around one thing, the chance that any one data science project ultimately yields a successful outcome goes way up. So what we're seeing is that teams that tend to identify and focus around their customers and start and end all of their data science projects with the customer, they tend to do a lot better than those that do not. So this means thinking holistically about customers. In some cases, it may very well be the end user or your company's customer, but a lot of the time it's internal employees that will be consuming the work that we're doing as data scientists. So if it's a dashboard we're making or a chart, there's a user of that dashboard or chart, and thinking critically about how technically savvy is this person, how likely are they to modify the report, do they need to see it at a glance, and same goes for self-service decision tools that are going to be used in-house by a sales and marketing team, as well as customer-facing requirements and so forth. So building upon that, we can kind of expand. What does a customer-focused data science organization look like? Well, for starters, empathy for the customer and deep understanding of the customer's pain, and understanding what it would mean for whoever this constituent is to have a solution to the problem is incredibly powerful. The chance that you build something that they don't want, if you fundamentally understand and empathize with the situation, is pretty low. People want, if you're aligned around the same vision of a solution, pretty much the chance to build the wrong thing goes down. Another really, really important attribute of any successful data science organization is that they care a lot about the practical constraints in which a solution needs to operate. So this could mean data being available is a really common one. If you fit a model and it is performing really well, but it relies on data that you rarely have available in your database at the time whatever decision you're making needs to be made, it's not such a good model because it isn't actually that practical. Same goes for models that are designed to create better user experiences. You need to take into consideration page load times and performance of the web app, and a lot of apps call for security considerations, etc., that may limit or constrain the viability of a certain approach to building whatever solution you are building. The third feature of data science teams that tend to be very successful is that they start really small with very low risk projects, and they tackle them with great efficiency. And this is incredibly important because it goes back to getting alignment among all of the different teams that need to be plugged in to really commit to building a data science organization from the get-go. And everybody seems to be able to align most of the time on end user facing stuff. So being able to put something into production, show it to normal people who are not sitting around thinking about machine learning all day, is one of the most powerful, if not the single most powerful thing that you can do to exhibit the benefits of something that basically most of the world doesn't even know about. And a fourth is if you can measure the impact of whatever projects you roll out, and it sort of becomes a data speaking for itself situation. So if you're building a recommender system and the goal is to get people to add items to their cart more often, measuring the propensity of people to put items in their shopping cart is a great way to show anybody, regardless of their technical proficiency, to get on board and commit to further investment and expanding the project scope, etc. And then the last one is iteration. So if you have a big vision for what you want to do, and you want to get there as quickly as you can by starting small, it necessarily implies that you need to relentlessly iterate, and to do so sort of in the same spirit that agile software development teams operate with, sort of a feedback loop, and creating a really tight feedback loop between the core constituents and obviously ideally the end customer that you are solving a problem for. So these 5 things are, I'm sure there could be others depending on organization that might be especially particular that you'd insert either above, below, or in between some of these, but I think universally the spirit of these 5 attributes is pretty consistent across the most successful data science organizations that we talk to all the time. And the top 2 are sort of core to the businesses of the particular team that you're talking about, and are going to be highly nuanced, right? Nobody's going to help you understand who your customer is. That's something that you need to do yourself. But we think that there's an opportunity to solve some of the problems down here in steps 3, 4, and 5. And that's sort of what we built our organization around philosophically. How can we help data science organizations start small and ship quickly, measure the impact of the projects that they roll out, and iterate faster. And so that's what we're going to talk about for the duration of this webinar. And I'm going to actually turn it over to Colin, who runs our product team, to give you a quick demo.
Cool. Thanks, Austin. So before we launch into the demo, I'm kind of just going to briefly set the stage and reiterate some of the points we made a little bit earlier, and address how some of Yhat software solves this problem. So here again, we have the very familiar problem. We have a bunch of R code, we have a bunch of statistical methods, and ideally, a data science team or team member has come upon like a solution to a problem. They then present it to their manager or maybe someone higher up, who then, it looks like code, it smells like code, so let's get it to the dev team. So from that point, the data scientists will go talk to someone in engineering, and here's kind of where you see this divide occur, where sure, it's code, but data scientists have tools, libraries, packages, specialty sort of items that are unique to their kind of skill sets that are completely different than what an application developer might be using to program in. So when you see this situation, when can I go live with my new model, we encounter a whole host of issues. One of which is code. So how do we take a language that is scientific and make it work with application focused languages? And then furthermore, how do we take a team of data people, data scientists, and incorporate their work into the deployment lifecycle or like the engineering workflow, and find ways to insert their work into the engineering kind of schedule, if you will. So this is where you often see the throw it over the wall projects. Data science will wrap up what they perceive to be a solution and then say, hey, engineering team, I've got this model. It predicts X, Y, or Z. Here it is. Let's put it into production. And from that point, you basically see a transfer of ownership from the data science team to the web application developers. And it basically depends upon them to both put into production, maintain it, and kind of ensure that it works. This is obviously a super inefficient process. It can take anywhere from weeks to months to if putting data science into production is never a priority for engineering, you can have a model that will sit on a shelf and never do anything. So what we aim to do at Yhat is solve this problem. So the way we solve this is be using REST APIs, which allow data scientists to write code in scientific languages that can be interacted with in this kind of standard compliance way that application developers understand. So now I'll introduce the idea of ScienceOps, which is the product that kind of embodies that cloud API endpoint on the previous slide. So the way this kind of workflow works is you have a data science team over here on the left. They deploy or send their predictive models to ScienceOps, where they're hosted across a distributed architecture. And then those models can be invoked or queried from a whole host of, it could be applications, it could be customers, marketing teams, frontline employees, basically anything that can make a REST request. So super standards compliant, really easy to interact with, and basically facilitating getting data science insights available to employees and customers across your company. So with that, I'm going to jump into the demo. We're going to use R for this first example. Know that Python is also a language we support as well. So this, the model that I'm going to showcase here, this is a lending model. For those who are familiar with fintech use cases, it's a super standard problem. If you're a company that issues loans, you need to be able to assess the riskiness of an applicant. So I'm not going to dig into the details of the model. This kind of goes back to the slides where the value of transforming raw data is not very high. But we'll dig in here at the very bottom here. You can see I've constructed GLM, which is just a linear. This is a logistic regression. You can see we're taking in like 3 or 4 different inputs about a hypothetical loan applicant, and then we've trained our model. So from this point, if we think back to the throwing it over the wall sort of methodology, we would be stuck with a logistic regression that we may not be able to implement into production till months down the road when engineering finds time to do this. So that is where, again, Yhat comes in. So below this series of hash marks, you can kind of see how the construction of the API endpoint works. I basically build something called model.predict, which is at the core of the API. So any request that comes into my model is going to be sent to this function. It's going to execute. You can see some kind of simple transformations we'll do here, and then it's going to send back output to the requesting body. So what I'm going to do from this point, I'm actually going to deploy the model simply by just running this code. So I'll run it. It takes a little bit to train the model and all of that. But in the meantime, we'll jump over to the ScienceOps UI. So just taking a step back, this is the model overview page. All the models that I deploy to ScienceOps will appear here. You can see here I have the Lending Club model that I just deployed. And from here, this is, for those who are not super familiar with REST API endpoints, you can see how how a REST endpoint would work. It takes in JSON, which is just a data structure over here on the left. And then my model produces an output over here. So by clicking this execute model, if you watch this Yhat ID in the right corner there, you'll see it change each time. So this kind of emulates a user or an application sending a new piece of data into my model here. We can, for just example's sake, see what someone with a slightly higher credit score would produce. Just watch the values here, and we'll see that it looks like they're much less likely to default. So we can see we have a somewhat functional model here. The next kind of part, we've deployed our model, our REST endpoint is ready. How do we then integrate with our engineering team? That's what this this integrations tab is for. We have a whole host of basically simple code snippets where you could copy this information here, hand it over to a developer, and begin kind of having an application query this model that you deployed. So a super simple way to kind of make the handoff to engineering even easier than before. Versions, this is another really important part of the functionality that ScienceOps provides. Again, looking back, every single time you see a change in your data, feel the need to maybe integrate with another third-party application, make a modification to a model. Every time you do that, you incur a cost of having to re-implement that into production code. One thing that ScienceOps allows you to really do very gracefully and with minimal cost is just version very rapidly. So as I keep the inputs and outputs of my API the same, I can retrain my model. And you can see here, I've deployed 8 different versions that are all, statistically nuanced and different, but the application that queries them can still get the same response there and back. So a really, really nice way to update my models without having to kind of go about like a whole engineering or re-engineering of a task. With that, I can also redeploy old models. So by clicking redeploy here, the previous model will be put into production. There's no downtime between the switching. So if hypothetically consumers were querying my model during those 2 or 3 seconds there, they would still be receiving predictions during that switch. You can look at model logs, not terribly exciting, but useful for debugging. Unit testing, another really important thing to consider when productionizing models is you have to kind of think about the productionizing as mapping to what would an engineer expect this model to do. So unit testing, and those of you who are familiar with engineering best practices, is a very common thing. So what we allow you to do is upload a test here. I don't have any on hand, but upload a test, run through a set of inputs, confirm the outputs meet the necessary requirements that you specify in the unit test. And then if all of those checks check out, then the model will build and be put online, and then the API endpoint will address that latest version. So just another way to kind of confirm your model's efficacy. Model settings, not super exciting, but just another way you can control kind of the ScienceOps environment. I'll jump over to the admin page here. So here you can administrate users. These are all the different models that we have currently running. This is the sandbox environment. And then there's systems monitoring information. So here I can see the workers. This is a distributed system, so I have 2 worker nodes and a master node. I can see that the CPU usage is fine and check into that. I can modify the environments where my models are deployed to. So if you have proprietary packages, custom libraries, anything like that, you can modify all of that through here. Monitoring, kind of as I mentioned, another best practice that you see in engineering departments. We have the exact same thing built out for ScienceOps. So Graphite is a really common tool for monitoring systems, models, servers, kind of network I/O. All of that information streams directly from ScienceOps into Graphite. So whoever takes ownership of model monitoring, systems monitoring, all of that is kind of taken care of through Graphite. We also have Nautios configured optionally as well. And then lastly, prediction logging. So another really important consideration when productionizing predictive models is once your model goes live, you need to be able to know whether your model is generating predictions successfully or generating errors. And then even more importantly in the long run is how has my model's efficacy changed over time. So if I deploy a model on January 1st, is my model still statistically relevant in February, March, and what about April? How do I begin to kind of look into my model as it's live and kind of experiencing the real world of streaming data? So that's where kind of predictions logging and monitoring comes in. This page here lets me just see a system overview, so I can see how how many predictions are going through on an hourly basis. You can see here, this sandbox has had 26 million predictions go through in the last, looks like 20 days or so. And we can see here just like a brief overview on the error rate. So, you know, a 13% error rate. Most of these are kind of demo models, but if you saw a spike in your error rate, you would maybe take that as an indicator that maybe your model is miscalibrated or something like that. We also can look up individual predictions as well with this unique identifier down here. So that kind of wraps up the demo. At this point, I'll hand it back to Elise, who can lead us into our Q&A.
Great, thanks, Colin. So feel free to continue to send me more questions down in the bottom right. For now, we've got a few to get started with. And if we don't have time for them all today, of course, feel free to follow up by email. So the first question that I got is, can the software be installed on-premise?
Yep, great question. So our software can ship and install basically anywhere. We have customers who are running it on raw metal, if you will, in a physical server in their data center. We can install in a VPC like Amazon, or also Yhat can host a version of ScienceOps specific to your company.
Perfect. All right, another one that we had come in. How do you deal with increased throughput to models?
Good question. So ScienceOps scales horizontally in two different ways. One from a hardware level. So the cluster that I've demoed on right now is a 3-node cluster with 1 master server and 2 workers. We can expand out the number of workers very, very extensively to allow for further replications of models to exist. Additionally, you can create replications of models on individual worker nodes. So the lending model that I deployed earlier, if we experienced high throughput, we could increase the number of lending club models, if you will, on the system within the hardware that's currently available.
Great. All right, another question that we hear pretty often. Can we use custom packages in environments?
Yes, so all the tools and functionality that you can use in R and Python are all available just natively within ScienceOps. For custom packages, custom C bindings, any sort of libraries that are proprietary or you've created yourself, they can all be put on the platform and accessed from scripts as well.
Perfect. All right, another question we had come in. Can these models be continuously trained and updated? And if so, does that create a new version of the model?
Yes, so the training and updating of models, the way we treat versioning is each time you retrain a model, it's a new version. So it may not change in its structure, but if the data has changed that the model is seeing, that is a new version. For automated deployments, we recommend using, we have a couple best practices in our documentation on how to do that on an automated basis. So you can read about that there.
Okay, just going to give this a few more seconds to come in. All right, it looks like we're not receiving any more questions at this time. If you'd like to follow up with us, you can email Colin, and that's just colin@yhathq.com, or myself, and that's Elise, E-L-I-S-E, @yhathq.com. With that, we'll wrap up. Thank you, Austin, for the intro to applied data science, and Colin for the demo, and thank you all so much for joining us today. Have a good one.